So where we left off the previous question was asking some questions about what if we have multiple forces that don't act in the same direction or in opposite directions. So what if we have forces that are acting in two different directions at the same time? So here I have my stoplight and it's being suspended by two cables. One is at a 35-degree angle with the horizontal and the other one's with a 43-degree angle with respect to the horizontal. So if I draw my free body diagram, I'm going to call T1 the more horizontal of these two cables, the 35-degree angle one, T2 the more vertical, the 43-degree angle one, and then I have weight mg pulling me downward. Now when I go to apply Newton's first law, one of the things that I'm going to run into as a challenge in this particular problem is that I can't just say T1 plus T2 equals weight. The reason for that is T1 and T2 are not pointing in exactly the opposite direction as weight. So what I'm going to need to do is break things up into x and y components and figure out what's happening horizontally to the forces and what's happening vertically to the forces. We're in the x direction and the y direction. In general, x does not always need to be horizontal and y does not always need to be vertical. As long as x and y are perpendicular to one another, you can do this technique. In this problem, I think it does make sense to make x horizontal and y to be vertical. Other things that I look for are two of the unknown forces or two of the forces in the problem perpendicular to one another. If the answer is yes, I generally will make one of those forces x and the other one y. So to write this out, what I have is the x component of T2 minus the x component of T1 gives you 0. The y component of T1 plus the y component of T2 minus mg gives you 0. So I need to figure out what do the x and y components of T1 and T2 look like. So if I have T1 here, T1x is really this side of this right triangle in here. And so T1x and T1 are related to each other by cosine. In fact, I could say the cosine of 35 is T1x over T1, or T1x equals T1 times the cosine of 35. I can do the same thing with T2x, that I have this right triangle, that T2x and T2 are related to one another by the cosine of 43. Now for T1y and T2y, they're related to each other by sine. So T1 sine of 35 is going to be T1y, T2 sine of 43 would be T2y. So if I plug all that information in there, I now end up with my system of two equations. I'll give you a minute to kind of copy that down in your notes. Now the one thing to remember with this system of equations is that we really only have two unknowns at this point, T1 and T2. Unfortunately, this system of equations looks fairly complicated because we have a lot of these sines and cosines, these other functions in there. So we're going to go and solve the system of equations, and the general technique that I use to solve the system of equations is what I call substitution. So I solve one of the equations for one unknown. In this case, I'm going to solve the one on the left. And so I add T1 cosine of 35, and I divide by the cosine of 43. The reason why I chose the equation on the left is it looks a little bit easier to solve than the one on the right. And then I substitute it into the other equation for T2. And when I do that, what I have is only one unknown, T1. I know the mass is 50 kilograms, I know G is 9.8, and really all those sines and cosines, they're ultimately numbers that I can calculate in my calculator. So I'm going to add mg to the other side. I'm going to factor out T1, since T1 is in both of those terms on the left-hand side now. And then I take cosine of 35, divide by cosine of 43 times sine of 43, and add the sine of 35. And I'm going to get T1 times 1.337 equals mg. From here I can solve for T1. It's mg divided by 1.337, so 50 times 9.8 divided by 1.337, or 366 newtons. So what can I do with T1? I can now substitute it in for T2 and solve for T2, and I get 410 newtons as T2. So these are the two tensions in the two cables. So one of them is 410 newtons, one is 366 newtons. The thing to remember is the weight of the stoplight itself is 490 newtons. Now you might be scratching your head saying, well, why do T1 and T2 not add up to be the weight? What you've got to remember about T1 and T2 is not only are they supporting the weight of the stoplight, but they're also pulling horizontally against one another, really in some ways supporting one another at these two angles. So let's consider this 50 kilogram stoplight supported by two cables. As shown to the left, are the tensions of the cables the same? No, they weren't. Which one was larger? The more vertical cable was larger. And do the tensions add up to be equal to the weight of the cable? No, they don't. In fact, they add up to be more than the weight of the cable because they have to pull on each other. The next problem that I'm going to do is a really common problem and one that shows up in a multitude of variations in physics. And this is what I call the block sitting on a ramp problem. So you have a 10 kilogram block, it's sitting on a 30-degree ramp, and I want to find the magnitude of the frictional force and normal force that acts on the block. So I have a free body diagram, weight or gravity pulling me down, friction up the ramp, normal force perpendicular to the ramp. I'm going to say sum of force in the x direction equals 0, sum of force in the y direction equals 0. Now, normally I would say x and y is horizontal, but in this particular case, two of these forces are perpendicular to one another. Friction and normal force are perpendicular to one another. How we know? Friction always acts up the ramp, and normal force is perpendicular to the ramp. So they must be perpendicular to one another. So I'm going to call x the direction up the ramp, and y the direction perpendicular to the ramp. What this means when I plug in my forces in my equation is I have friction minus the x component of weight equals 0, and normal force minus the y component of weight equals 0. So if I go to break up weight into its components, here I've put on my free body diagram the x and the y component of weight. It looks like the x component is opposite that angle, 30-degree angle. Y component is adjacent to that angle, 30-degree angle. And so I could get friction minus mg sine of 30 equals 0, normal force minus mg cosine of 30 equals 0. It's worth pointing out this angle in here between the weight and the y component of the weight is actually always equal to the angle of the ramp. You can prove that by using some trigonometry if you'd like to. Weight goes straight downward, so it's perpendicular to the bottom of the ramp, so this angle here would be 60 degrees. The y direction we said was perpendicular to the ramp, so this whole angle would be 90 degrees, so 90 minus 60 gives you 30. So here let's solve out, I guess we can solve for both the frictional force and the normal force right away without doing any substitution. Frictional force is mg sine of 30, normal force is mg cosine of 30. We can plug in m and g and solve it out. So 49 newtons is the frictional force and 84.9 newtons is the normal force. It is worth pointing out that these two forces do not add up to be the weight of the block, mainly because the normal force is really doing a couple of things. It's not only supporting the weight of the block, but it also has this x component down the ramp. The frictional force is really holding the block on the ramp to prevent it from sliding down the ramp. So some general strategy for equilibrium problems, and we will practice this for a few days in class. Draw the free body diagram. Choose an x and y axis. Set up your equations for Newton's first law. Do some algebra to solve for the unknowns. And finally, your last step is to calculate your answer. And so that's kind of the general technique for solving equilibrium problems.